This is Statistics 243 for Wednesday, October 29th at Berkeley. Okay, let's go ahead and get started. So, the first thing I wanted to do is to talk a little bit about this rough proof of this result here, that the relative error in getting the solution of a system of equations, of solving AX equals B, is going to look something like the condition number of the matrix A times this value where P is 16, and comes from the numerical inaccuracy in representing numbers on a computer. So we'll spend a few minutes just talking about that, and then we're going to spend the rest of the time talking about solving systems of linear equations, and we'll use that basically as a way to, by talking about it first as solving a system of equations, we'll sort of use that as a way to get into doing matrix factorizations, and in particular to thinking about how do we count up the number of operations for these kinds of procedures, and how do we think about the effects of numerical inaccuracy on a computer and the impacts of that on doing these sorts of things. Okay, so we saw last time that in some cases when A has a large condition number, we saw that if we change B a little bit, that can result in big changes in the true answer X. This is just if we were doing this as a mathematical problem. And then so we saw that example, and then the idea is to relate it to what if we're actually thinking of this as a computer arithmetic numerical accuracy kind of problem, where the system that I'm really solving on a computer is this, because I can't actually put A in. I can't actually work with A, work with B, and work with X exactly because of the fact we only have 64 bits to represent the values in those matrices and vectors. Okay, and so I guess at last time I waved my hands and I said, okay, this is the result that you get that says the error in your solution.
Sorry.
No worries. Is approximately equal to this, and so if our condition number is large enough, so this is 10 to the minus 16, if our condition number gets to be 10 to the 12, 10 to the 14, 10 to the 16, all of a sudden we essentially have very little accuracy in the answer that we get, because the answer that we get is going to be x plus delta x, and this says that if the condition number were 16 and this were 10 to the minus 16, which it is, this would be about 1. The ratio of those two magnitudes would be about 1, and we're basically saying the magnitude of the error is approximately the same as the magnitude of the x that we're trying to find. Okay? And that's obviously a big problem. Okay, so questions about the setup here? Okay, so as you guys are coming in, I was writing out the basics of what this proof looks like. And I'll pause. Well, let's see. Let me pause for about 30 seconds, have you guys try and absorb some of, just get a basic sense of what's going on here. And as you're looking at this, try and remember, think about the reasoning for why we can go from this step here to the norms. And try and think about when this would be the case that this quantity is approximately equal to 1, and how that relates to the condition number. What I'm writing over here is totally unrelated. Okay. Okay, so here I'm just expanding out the terms. And then I'm just rearranging and throwing everything on the right-hand side. Why am I getting rid of this? Because x equals b in the mathematical result, so those two are the same thing mathematically, so that's 0. This term should be in here. I'm not going to carry it forward, but basically you can do similar manipulations with this term as we're going to do with all of this, and basically show the result is the same. So just for the sake of just sort of seeing some of the kinds of arguments that come up here, just as a review of some of the linear algebra, I'm going to ignore this. But if you play around with this, you can see that this term doesn't affect what the answer is, even though it's basically another constant that gets that would get sort of added in here. So it would become like 2 here instead of 1 or something like that. And so it doesn't really impact the sort of order of magnitude of things that we're doing here. Okay, so we know A is invertible because we're solving the system of equations, so we're assuming that. So I'm just multiplying by A inverse here, and the result is I get A inverse here, and I can write this like this. Okay, so what facts am I using to go from there to there? Alex? Okay, so where's the triangle inequality come in? Okay, so the triangle inequality comes in because basically in going from the norm of this being less than or equal to the sum of these two norms. Right? What's the other fact that's coming in here, sort of in some sense even before I get to that?
There's the fact that the normal product of matrix is lower than the norm of the product.
Yeah, so we're also relying on if we have something like this, the norm of a product is less than or equal to the product of the norms. So I'm basically doing that 3 different times here. So the minus is going to disappear because I'm talking about norms, which are just magnitudes. So I'm going to get the norm of A inverse, the norm of delta A, the norm of this whole quantity, and then there's the step that Alex said, okay, then I'm also going to use the triangle inequality. And so then I've got this as my resulting inequality. Okay, so now if I sort of know where I'm trying to get to, this is sort of I can sort of see why I'm doing this. If you were sort of proving this without knowing the result, you might not think of this for a little while. But I know the result I'm trying to get to involves the product of the norms of these two, A and A inverse. So I'm just going to introduce an A and an A here in the numerator and the denominator. Usual story in a number of statistical proofs. So now this thing is this condition number, right? We said last time, I'm actually asking you this on the problem set, I'm not sure yet, that this is going to be the ratio of the largest and smallest eigenvalues of A. Now we've got delta A over A, which is something we know that we want to have in, or let's see, no, that's not something we want to have, but that's actually going to disappear eventually. But so let me retract that statement. But anyway, we have delta A over A. That's just the result that's in. That's just necessarily so. And now we're going to do a little bit more rearrangement. And basically, if we just do some multiplication and move some terms around, what we'll get is we can get this piece on this side, basically moving the delta x piece times this over to there. And now the interesting thing is that I guess we are sort of trying to get here. I was forgetting about the relationship between that and this. Now we're almost there, right? If we look at this, we say, okay, well, if I could just divide by x, I've got delta x over x here. I've got my condition number here that I want, and I've got this delta A over A, which I've sort of waved my hands and said is roughly 10 to the minus p because of what we know about computer arithmetic. So the only question is sort of what is this, and is this actually around 1? If this is around 1, then we're done. Then we've got this as a result, and that's the same as what I'm writing up there once we have that this is around 10 to the minus p. Okay, so under what conditions is this going to be more or less 1? So G, do you have any thoughts here? So we know this is around 10 to the minus 16. Julie?
Is it if K of A is 10 to the 16?
Well, if it were 10 to the 16, then it would be 10 to the 16 times 10 to the minus 16, 10 to the 0, that would be 1. So this whole thing would be 0.
Oh, so it has to be
Right.
sorry.
The other way around.
Yeah.
Okay, so this would have to be small relative to that, right? So all we're saying is that this this result, which I've sort of framed as an approximation here rather than the lower bound, this result, and it's probably better if we actually change this. Yeah, I should probably change this to well, if the lower bound was fairly tight, and then we have this approximating step where I'm going to say this is about equal to 1, then we'll get that this is the approximation that we're getting. So basically what this is saying is this rule of thumb about how the accuracy of solving these equations on a computer, this rule of thumb works if the condition number doesn't get too big. So if this were 10 to the 8th, and this were 10 to the minus 16, this is 1 minus 10 to the minus 8, that's essentially 1. As long as this condition number doesn't get to be anywhere, it doesn't get to be close to 10 to the 16, then we're okay. So it's 10 to the 14, 10 to the 12, 10 to the 8, things like that. So the result holds as long as the condition number doesn't approach, as long as the condition number is rather less than 10 to the 16. So as long as we're not too ill conditioned, this can serve as sort of a rule of thumb of what we get for the numerical accuracy here. Okay, so I think I just wanted to show that you can basically get there using just some fairly standard linear algebra kinds of things and just sort of thinking about the quantities that are involved in the calculation. Any questions about that before I move along? Okay, so the next thing I want to talk about is how we would go about solving a system of equations. And I'm going to do that, and I want to do that for two reasons. Basically, one, we're going to see that solving a system of equations by Gaussian elimination is equivalent to doing an LU decomposition. And I didn't write all of the factorizations up again, but I did write 2 of them that we're talking about today and on Friday. And I want us to see that we can count up the number of operations when we do these kinds of factorizations. And I want us to see that the kinds of numerical issues that can arise when we do these kinds of calculations. Okay, so the next thing I wanted to do was to talk through solving a triangular system. And so part of the game here is going to be, for a lot of these different problems, the way we're going to get to being able to do things easily is we're going to try and take a problem that looks hard, transform it into a problem that involves triangular matrices, and then dealing with the triangular matrices is going to be straightforward. So what I'm first going to do is say, what if we start with a triangular matrix? We'll see that that's easy to deal with. And then the next step will be, how do we transform a problem from a full matrix to a triangular matrix? Okay, so we're going to start with solving a system of equations where we have a triangular matrix. So this just corresponds to the system of equations where I have a11 times x1 plus a12 times x2, etc. equals d1. And then I have a22 times x2 plus, etc. equals b2, and so on down until I have ann xn equals bn. So this is just writing it out so we recognize that this is a system of equations. It happens to be one that's easy to solve because of the fact that we only have 1 term in this equation, and then 2 terms in the next equation, and 3 terms, and so on and so forth. But this is the matrix representation of it. So solving this set of equations where I have an upper triangular matrix is called a back solve. The reason it's called the back solve is I'm going to work from the bottom up, so that's the back in the back solve. And I'm just going to solve this in the way that you would have seen in whenever, in high school or earlier on. Okay, so what's xn? Well, xn is just going to be bn divided by ann, just solving that simple equation. And then xn minus 1, since there's all this, all these subscripts floating around. So I think the hardest part of a lot of this is just keeping track of the subscripts and just the bookkeeping. So just sort of be aware of that. I'm going to try not to do it too much on the fly here and write it down, because I'm probably going to make a mistake if I try and do it on the fly. So we've got, let's see, what do we have here? We have bn minus 1 minus a n minus 1 and xn divided by a n minus 1 n minus 1. Okay, so now once we know what xn is, we can then look at this second equation, which I haven't written out. We can then solve for xn minus 1. It's going to work out to be this. I can work my way up, and if I represent each of the equations that I'm then solving for, they're going to look like this. xk for any given x in here is bk minus this partial sum divided by the divisor, which is the diagonal element for that equation, or for that row. Okay, so that's fairly straightforward. You guys could have just told me that was how we should proceed in this case. The interesting and useful thing about this is now to start thinking about counting up how many operations we have to do here. Okay. So before we try and write down exactly how many calculations we have to do here, let's just step back and say, okay, intuitively, how many do we think we're going to have to do? So I said last time, if we're doing matrix multiplication, there are 3 for loops. It's order of n cubed. If I'm doing matrix vector multiplication, it's going to be 2 for loops, so that's going to be order of n squared. So how many for loops are there here? So what's the first loop that I'm doing here? What's the outer loop?
Oh, the in loop.
So the outer loop is working my way up here, right? And what's the inner loop? The inner loop is for any given xk, I've got to do a for loop to do this sum. Okay, so 2 loops should be order of n squared. Okay, which also sort of makes sense because we have a matrix. We sort of have a matrix vector operation here, so that also sort of goes along with this idea that it's n squared. If I do a full matrix vector multiplication, this is going to be n squared, exactly n squared multiplications. So it's not only order of n squared. The constant in front of the n squared is actually a 1. Because I've got n multiplications here, n here, so it's actually going to be exactly n squared. Anyone want to take just an intuitive guess as to what the constant should be if I'm gonna do this? And pay attention to what this matrix looks like compared to what this matrix looks like. Yeah. Okay. So you said it aloud, and you said it without actually saying it. It's a half. Yeah. It's good. This is going to turn out to look like n squared order. I don't know if I want to say order because there's a 2 in here, but it's going to be n squared over 2 plus some term involving some term involving n. Okay. So it's going to be n squared plus some term involving n. Okay. So we can actually just go ahead and count this up and make sure that we get the right answer. So I'm going to pause for a minute and have you guys try and actually write out yourselves how many multiplications or divisions am I doing in each of these steps, and then add them up and see what you get as the result. And before you do that, let me just pause and say, if I look at these calculations, obviously there's a division here, there's a multiplication here, and a division here, but there's also some additions and subtractions. And then what I'm going to tell you to do is only count up the multiplications and the divisions. And there are basically 2 reasons for that. One is that in essentially all of these kinds of calculations, an addition or subtraction is paired with a multiplication or a division. So if you just count the multiplications of the divisions, it's sort of redundant to also be counting the additions and subtractions. So we'll just ignore those. The other is that if you delve into how the computer does the calculations, it's more expensive to do a division or a multiplication than it is to do an addition or subtraction. So that's another reason we're just going to leave aside the additions and subtractions and just concentrate on the multiplications and the divisions. Okay, so take a minute or so. Feel free to consult with your neighbors. Try and add up explicitly add up and count up how many how many multiplications and divisions there are. And what we should see is we'll get something that's n squared plus something that's order of n. N squared over 2 plus order of n. Okay. Anybody get the full answer?
I can guess. I'm
Okay.
understanding right. Is it n times n minus 1 over 2?
That sounds about right. It's either that or n times n plus 1 over 2. N times n, yeah, n times n minus 1 over 2. Okay, so why? So I've got one division here, so I can sort of work my way up. I've got one division here. I've got how many multiplications and divisions here? 2, right? There's a division and there's a multiplication. So 2. If I sort of work my way through the indexing here, what I should see is there's one division and there are 2 multiplications there for the third equation up. So that's a 3. And if I keep working my way up, I should see when I get up to the top one that there are n up there. Yeah.
So it's n plus 1.
Yeah.
Is it n times n plus 1 over 2?
Yeah.
Okay. So why?
If you count division and multiplication separate.
Oh, okay, yeah. Yeah, I was thinking, sorry, yeah, it's n plus 1 over 2. I think on here, I was reading off here that I'd also separately, just for my own interest, I count up the addition and subtractions, and that's n times n minus 1 over 2. But yeah, thanks for catching that. Okay, so this is, obviously what this is. This is 1 plus 2 plus 3 up to n. Did I erase it already? Oh, I guess I already erased it. So there's that old formula you guys have probably seen before, that the sum of x equals 1 up to n of x is n times n plus, capital N times n plus 1 over 2. Okay. And we're also going to see that we're going to need, for other things later in the next couple days, we're going to need to be able to know what, I think, is that what I need? I'm going to need to know that as well, and I have that written down somewhere that I will come and find it when I need it. Okay, so this is order of n squared. If we're interested in the constant, it's 1/2, and then we're ignoring the term that's just n over 2 because that's of lower order of magnitude than the n squared term. Okay. Any questions or comments? Okay, so let's now start to talk about the fact that in most cases we are not going to have a triangular system at hand. Actually, no, before I say that, let me just say a brief comment about doing this on a computer. So if we were to do this in R, I'm just creating an X here that is full rank and invertible. And I'm going to create, let's see, this is just for the sake of this illustration. I'm creating an upper triangular matrix U and a lower triangular matrix L, but you can sort of ignore where they come from. But assume I have an upper triangular matrix or a lower triangular matrix, and I want to solve either UX equals B or LX equals B. If I have an upper triangular matrix U, then I do the backsolve by just calling the backsolve function on U and B. And if instead I had a lower triangular matrix, then I would be solving the system of equations that looks like that. And that's just called a forward solve because I would start from the top and work my way down, but it would basically be the same calculations. And so if I had a lower triangular matrix L and I wanted to do that solution, I would do forward solve in R. And those things are equal. Those things are going to be equal to if I actually explicitly invert the matrix, which is what U is here, which is what I'm doing here with the solve function. That'll explicitly get U inverse. Or if I explicitly invert L and multiply it by B. But doing it as the back solve or the forward solve is much more computationally efficient than actually explicitly inverting this matrix, because inverting the matrix is going to be order of n cubed. And what we saw here was I only had to do order of n squared calculations to do the back solve or the forward solve. And then it also turns out that if we happen to have, if we happen to want to do these calculations without actually, if we had U but we wanted to find this, we don't actually have to explicitly do the transpose first. We can actually just call this back solve function with transpose equals true. So oftentimes we don't necessarily have to do the explicit transpose. Okay, and then I've highlighted this in bold. I'm going to say this multiple times, but when we're thinking about finding AX equals B or UX equals B, if we have some upper triangular matrix, even though mathematically the answer is that X equals A inverse B or U inverse B, that doesn't mean that on a computer we go through step by step and say, oh, I'm going to invert A and then multiply by B. Okay? It means that this is, as we think about it on a computer, this is sort of shorthand for I'm going to go ahead and solve this system of equations by an appropriate method, not that I'm going to go ahead and actually invert the matrix. Okay. So now let's turn to what if we just have a full matrix A that's not triangular. So the name of the game here is going to be we're going to take this system of equations that is with the matrix A and we're going to convert it to a system of equations that looks like this, where we have an upper triangular matrix. And then we've already done the rest of the problem. So all we're going to do here is Gaussian elimination. You guys presumably saw Gaussian elimination at some point. As usual, I'm not quite sure when we learn a lot of these things because I've just sort of forgotten it. But we're going to work through Gaussian elimination. We're going to see that it's actually equivalent to coming up with an LU decomposition where A can be expressed as some lower triangular matrix times some upper triangular matrix. So the main idea here is we're going to convert to a triangular system, and then we already know what to do. Okay, so Gaussian elimination. So we start out with this system of equations that we want to solve. I'm writing it out as the actual equations here. Okay, here I'm using lowercase a to mean the elements of the matrix capital A. And each of these pieces here is just a row of A multiplied by the vector x. So I'm just writing it as A something dot transpose times x, and that's another way of expressing this system of equations. Okay, so I don't know if you guys remember Gaussian elimination, but if I want to convert this to a triangular system, what am I trying to do? I'm trying to make sure that all of these coefficients in this row and then the ones in this column below the A1, and all of the coefficients here and all of the coefficients here and on down to here, I guess not that one, down to here, are zeros. Right? So I'm just trying to zero out the coefficients in the lower triangle of A. Okay, so as we all learned in algebra, I guess, we can take linear combinations of equations and preserve the solution x here. So what we're gonna do is in terms of doing Gaussian elimination is we're gonna make sure to take a clever choice of combining these two equations in a way that we're gonna replace the second equation with one where there's a zero in this position. And then the next step is we're going to do basically the same thing to the third equation and replace the A31 with a zero. And we're going to march down and replace all of these guys with zeros, and that will give us basically give us something where we have zeros down the first column. Once we've done that, we're now going to have an n1 by n minus 1 by n minus 1 matrix, and we're going to play the same game with the n minus 2 elements here and zero out these guys. Then we're going to zero out the n minus 3 elements here, and so on and so forth until we have a triangular system. Okay, so in order to do that, I just need to take some C1 times A1 dot transpose x plus some C2 times A2 dot transpose x. And that's going to be equal to C1 B1 plus C2 B2. And then I'm going to throw that in and replace the second equation with that. Okay, so C1, if you could work this out, it's not hard to work out, but just for the sake of time, C1 is going to be equal to minus A21 over A11, and C2 is just going to be equal to 1. So if we just work through the algebra of doing this, what we'll see is that will zero out, that will produce a second equation where we have a zero in this position. Let me pause. Any questions so far? Kelly?
So you said that this is Gaussian elimination is equivalent to doing LU decomposition. Why would you ever want to do Gaussian elimination on a computer instead of LU decomposition? Order. Oh, well, because this is order n cubed and LU are both n squared, right?
No. So, but I'm glad you asked the question. In order to get from A to L times U, that's an order n cubed operation.
Okay.
And you're actually going to show that on the next problem set. Once we have the L and the U, then to solve the equations and find x is order of n squared. But it's a two-step operation. First we have to do this, which is order of n cubed. Then we have to solve the triangular system, and that's order of n squared. And the order of n squared is unimportant because it's dominated by doing this.
So it's
and
n cubed either way.
Yeah, so this is n cubed, or writing it out this way is n cubed, but it's the same calculation. It's just a different way of looking at it. Okay, so let's see. So once I do that, I'm not quite sure how do I want to write this. I guess I will just, okay, so this, what I'm calling A221 is the new A22 from doing this first step. The value of that is minus A21, A12 over A11 plus A22. And the value of B21, which is the result of taking this combination of B1 and B2, is just minus A21 over A11 times B1 plus B2. And similarly, we could write that this is minus A21 over A11, A1n plus A2n. Okay, so so far what we've done with this linear combination is we've gotten down, we've injected 1, 0 into the system. The next task we have to do is inject this 0 into the system. And you won't be surprised to learn that we can do that by taking a linear combination of the first and the third equations and replacing the third equation with that linear combination, just like we do with the second equation. And so if we do that, we have that the C1 and C2 for when we combine the first and the third equations is the C1 is minus A31 over A11, and C2 is also 1. So we can basically just march our way down, inject zeros at each of these steps until we've zeroed out the first column except for the first entry. And as a result of that, we then have the n-1 by n-1 matrix here. Then we're going to move to injecting zeros here, and then we're just going to proceed onwards. But it's all these just sort of boring, tedious, keeping track of indices and working our way through the calculations. Okay, so once we've done that, we then have a lower triangular, A. The x's are sort of in here in a messy way, but we have a lower triangular A, we have an x vector, and we have a b vector, a new b vector. We can go ahead and solve. We can do what we talked about on the board over there. Okay, so it shouldn't come as too much of a surprise that if you sort of look at this carefully, what you'll see is there are 3 loops that you'd have to work your way through. Yeah, I guess I don't want to say anything more about that. It's going to turn out to be order of n cubed. You guys will work through the details of counting up the operations. Let's see. So the next thing. Oh, and so for that, you'll need the result that the sum, when you do this on the problem set, I'll write this on the problem set as well. You need the result that this is equal to n times n plus 1 times 2n plus 1 over 6 when you have x squared terms in there.
So there's not a package on it?
That will do this?
I mean, I just Googled it.
Well, basically what happens is if you do solve A, B, if you do that in R with A and B, it's basically doing the LU decomposition behind the scenes, so it's basically doing Gaussian elimination. So there is, it just goes by a different name. Okay. Any other questions? Okay, so the other 2 things I wanted to highlight by doing this were to talk about this as a form of matrix factorization and to talk about the numerical issues that arise. We may not get to the numerical issues, but let's talk about this as a form of matrix factorization. So it turns out that you can write what we just did. I'm going to erase these guys here. You can write what we just did as the following process. that the steps that we just talked about can be written as taking a lower triangular matrix that I'll call L1, multiplying it by A, taking the result of that, multiplying it by a lower triangular matrix L2, and when you pre-multiply by all these matrices, you get an upper triangular matrix. And it also turns out that when you multiply lower triangular matrices, you also get a lower triangular matrix, and that we can invert that matrix, and so basically A is equal to the inverse of these guys times U. Turns out this thing is also lower triangular, and therefore this is the LU decomposition. It's basically writing all this out. And the other nice thing about this is it sort of all pops out magically, which is nice. It turns out that L1 is equal to 1, 0, 0, zeros, minus A21 over A11, minus A31 over A11, minus AN1 over A11. And 1's on the diagonal, and 0's on the off diagonals here. Okay, so L1 amounts to the matrix that if we multiply it by A, injects these zeros into A. And then L2 is a similar sort of matrix that injects the zeros in the second column of A. And there are some instructors who seemingly to me can sort of magically manage the board such they don't have like this stuff here and that stuff over here and this stuff over here. I've never been able to figure out how to do that, which maybe indicates some shortcoming in my ability in my brain to manage things. But L2 is equal to 1, 0, 0, zeros here, 1, zeros, minus A32, the first sort of next iteration version over A22, down to minus AN2, 1, over A2, 1, and then 1's, 0, 0. Okay, so L2 basically amounts to, let me take an n-1 by n-1 matrix that looks just like what L1 is, and let me have 1 and zeros and 1 and zeros on the upper row and the lower and the left column. So those, and then you can sort of continue on, work your way on, and it's just basically gory bookkeeping to figure out, to see what the other L matrices are. And then the other thing that sort of pops out nicely is that because these L matrices are triangular, things work out really nicely in terms of multiplying them together and finding the inverses. And so it turns out that this matrix L is actually equal to the following. It's 1, A21 over A11, N1 over A11. 1's on the diagonal, and then A32, 1 over A22, 1. N2, 1 over A 2, 2, 1, and so on and so forth. So that's L. And U looks something like this. It's A11, so the first row doesn't change. And then the next row is what we've been calling these guys. And so on down to, so then we have A3, 3, 2, so on and so forth, and then we have A, N, N minus 1. And then we have zeros in the lower triangle. Okay, so all of the quantities that make up the LU decomposition are basically quantities that we computed along the way of doing Gaussian elimination, and they sort of go into place in a nice way. The other thing that I'll note here is that one of the things that people, when people were developing LAPACK and some of the other linear algebra routines, is they were often concerned with saving storage, particularly back in the days when memory was really a limitation. And so what you'll see if you look into the documentation is that if you notice where the zeros are in these two matrices, they're sort of conveniently, what's the word I'm looking for, aligned with each other. So I could actually, if I were doing the LU decomposition and I send the matrix A to a C or a fortran routine to do it, that routine can send the resulting LU decomposition back to me as a single matrix of the same size as A, because of the fact that I can just take the U values here, and I can take this matrix L. I don't need the ones if I know that the ones are in the diagonal. I can just take the lower triangle here and put it in here. And so I can represent the whole LU decomposition as a single n by n matrix, as long as I know which pieces go into which term in the factorization. Yeah.
So, would the package do the automatically permutation if it finds 0 pivot already?
If it finds what?
0 already. We're doing some permutation of the rows.
Oh, I see. So if it finds a 0, well, if it finds a 0, the only issue I think is going to be if it's trying to divide by a 0. Otherwise, if there's already a 0 there, I guess you don't need to do the computation. I'd have to sort of think through what happens if you do the computation, but I think it wouldn't be a problem. So I think the only issue is whether there would actually be zeros in the matrix, and I suspect that if we have zeros, it might.
I thought that was like a constraint on Gaussian elimination that all the diagonals have to be non-zero.
Yeah, that might be the case. I don't know off the top of my head what would happen there, or if that's something that we can assume is not going to be the case. Yeah. Other questions? Okay, so let's stop there. What we'll do next time is I'll pick up with this and we'll just work through actually now it's becoming more clear now that I look at my notes of what I want to talk about next. We will talk about Leigh's question of what happens if you have basically numbers that are trying to divide by that are very close to 0 and how we can avoid that, which goes back to this idea of pivoting, which I think you sort of mentioned. So yeah, so the thing we'll pick up with is how do we deal with if we're dividing by a very small number? We'll talk about those computational issues. And then we will talk about the Cholesky decomposition.
Yes.